Let's go ahead and do it. We're going to talk about parent functions. I know you've heard that word before, yes? In Algebra 2, have you heard that word before? You have. So a family of functions is a group of functions that have the same characteristics. So for example, parabolas form a family of functions. But we know that when it comes to the equations for a parabola, no two equations will look alike, right? Y equals x squared is an equation of a parabola. Y equals negative 2x plus 1 squared minus 5 is an equation of a parabola. Both of these give you a parabola. Y equals x squared is the default basic version of a quadratic equation. That is the parent function. And then everything else is what is derived from the parent function. Okay? So that's what we call a parent function. It's like the default, the basic case, period. All right, so we're going to go through every single type of function that we can think of eventually. And we're going to start with like 5 or 6 today. The first is a constant function, right? So a constant function, it looks like f of x equals c. So for example, f of x equals 3 is a constant function. You may have seen it look like, y equals 7. It could be f of x is equal to negative 4, right? That's a constant function. What could be a possible function for the one that's graphed over there for you? F of x equals what? Like 3.5, right? F of x equals 3.5. So if f of x is equal to 3.5, right? So basically what is that? Why is it a constant function? Because if I move from one x to the other, how does the y value change? It doesn't. It remains what? Constant. Hence the constant function. All right? So if f of x is equal to 3.5, then what's f of 2? 3.5. Right. And what's f of a million? 3.5. Right. Okay, and the end behavior? 3.5. That's a constant function. All right, next we have what we call the identity function, and that's f of x is equal to x, right? So this is f of x is equal to x. So now here's a question for you. When x equals 2, right, what's f of 2? 2. So what's f of negative 5? Negative 5. Do you see why it's the identity function? Because x and y values are the same, right? Whatever x is, that's what y is. So what does this function do? If you put in an x value, what does it give you back? The same x value, the identity, that same identity. That's why it's an identity function. Okay? Now, what else did you use to call this in Algebra 1? What type of function did you call this? A linear function. What's another example of an equation for a linear function? Yeah. Y equals mx. Right. Or if you put words in there, if you put numbers in there, f of x equals, let's say, 3x plus 2. Right? What is this? This is just a derivation of the parent function f of x. I took f of x, I did plus 2, which moves it where? Up. And then and then if you multiply by 3, what does that do? It makes it steeper. So do you see how any linear function is a derivation of the identity function? Yes. Right? So from here, we derive that. Okay, fabulous. Did you have a question, or was that it?
No, I was going to say, how would you get a vertical constant function? But then I realized that wouldn't be a function.
Awesome. Yep. Awesome. Okay, next let's move on to a quadratic function. A quadratic function, it looks like this, right? Where the x value is squared, right? So what does this function do? If you give it a value of x, what does it do to that value that you just gave it? It squares it. right? So when I give it a value of 2, it gives me back the square of 2, 4, okay? So if we're talking about functions, which is, if you move over, if you change the x value, how does the y value change? Let's think about that for a minute. If this is x squared, okay, so what are some characteristics? First of all, I know you all know this, it's symmetric, right, along that center vertically, yes? Okay, so is this an even function or an odd function? This is an even function, which means if you look at the end behavior, both ends of this go in the same direction, right? So both ends in same direction. That is a characteristic of even functions, okay? Now, let's think about some values here. If from this axis of symmetry, or the vertex, if I were to move over one value, 1 point, now I have a change in x of 1 unit, right? When I put that input into my function, the function squares it, and it increases the y by 1 squared, right? So, in other words, if I go over 1 unit, the y value increases by 1 squared, which is 1. So from here, if I go over 2 units, how much does it go up? 2 squared, which is 4. So if I go up here, if I go over 2, I go up 2 squared, which is 4. If I go over 3, I go up 3 squared, which is 9. Okay, so that's a quadratic function. All right, take a look at f of x equals x cubed. This is my cubic function. Now, is that an odd or an even function? That's an odd function. What does that mean if it's an odd function about the end behavior? They go in opposite directions, right? So ends go in opposite directions. Okay? Now, this function cubes my values. So, if I go from the center point to the right 1 unit, now that's movement of positive 1, right? Because I went over 1 unit to the right. So this is a shift of positive 1. My function cubes that, and I go up 1 cubed, right? Now, if I were to go over 2 in the positive direction, that's a shift of positive 2. My function will increase like 2 cubed, 8. Now, if I go over to the left 1 unit, that's a change of negative 1 from where I was, right? Because I went in the negative direction. So if I move negative 1 units, my y moves negative 1 cubed, which is also negative 1, so it goes in the downward direction. Do you see how it works? How the direction works? So if I go over to the left 2 units, how much of a change is that? Negative 2. So the y value will change as the cube of that, negative 8. Okay? All right. So that's a cubic function. Moving right along, another one of my favorites is the square root function. F of x equals root x. Okay, some observations here. Whenever you see a square root, the alarm should go off, right? So what alarm will sound? Right. What can't be a negative? The radicand, right? Cool. The radicand can't be a negative. So y equals root x. So then are we saying that x has to be greater than 0? So it can't be 0. Greater than or equal to 0, right? So radicand, that's what that's called. That's called the radicand. It has to be greater than or equal to 0. Okay. Which means, right, I can't just put any x value in there, can I? Which means its domain can't be all real numbers, can it? Okay. So what values are allowed to go in there? Only those values that will make the radicand greater than or equal to 0. Okay? So this function can exist only on those values which make the radicand greater than or equal to 0. So if it's the square root of x, clearly it's going to exist over, x equals 0 and up, okay? But now, what if I have the square root of 5 minus x? Right? Now what values am I allowed to put in there? Now all of a sudden negatives are okay to put in there, right? So if I put in like a -10, that's cool because when it goes in there, right? It's positive. Exactly. Okay.
Oh, but you can't have positives.
But now you can't have positives. Okay? Some, you can have some. So which positives can you have? You can have 0, less than 5, right? So now it doesn't exist on the right side anymore. Now it only exists on the right side. So what does that look like? That. You see that? It's completely flipped around. So we're going to talk about this in terms of a reflection, but think about it also in terms of why. Why? It's because it only exists over those values which make the function real. Yes.
Why do you only get...
So if you have y equals the square root of x, it only exists as your positive y values. Okay? So whatever value you put in here, like if you put in a 2, it just takes the square root and gives you the square root of 2. If you put in a 9, it takes the square root and gives you the square root of 9. Now, as opposed to, what you're thinking of is, if you started out with an equation that looks like this, right? Now that is different. Now you're being asked for the value which when you square gives you a 9. And clearly that can be two values, a 3 and a -3, right? So how does that work in the math? You take a square root of both sides and now you say, okay, x is plus or minus 3. But that's different. That's a different function. What function did you start with here? X squared equals 9. You started out with y equals x squared. Okay? So you had y equals x squared and you gave it a value of 9. This is y equals the square root of x. So they're two different functions. This is a parabola, which has a left and a right side. This is only a square root, which has one arm.
So what would the graph, wouldn't the graph just look like for this, what would the graph
The
look
square root?
like? Well, no, because it's x. Well, isn't it a y equals x squared? So wouldn't it be a parabola?
Y equals x squared would be a parabola. That is the case where if you solve it, you can get x equals plus or minus 3 because you have a parabola. But what we're talking about, if you're just taking the square root of 9, the answer to that is not plus or minus 3. That's just root 3 because that comes from y equals root x. And what does that do? Whatever function goes in there, it just takes the square root with no plus or minus.
So
Yeah.
If y equals root x,
So a reciprocal function looks like f of x equals 1 over x. Now, let's think about this for a minute. F of x equals 1 over x. First, let's think about domain, okay? Is x allowed to be positive numbers? Yes. Is x allowed to be negative numbers? Yes. What happens if x is like positive 5? What do you get? 1 over 5. What happens if x is negative 5? Negative 1 over 5. Okay, so is x allowed to be 0? No. No, x is not allowed to be 0. Okay, fine. Okay, can I put values in here for x, which will make y positive? Any positive number. Okay, so can I put values in there for x, which will make y negative? Yeah, so y can be positive, y can be negative. Can y, okay, what number do I put in there for y to be 0? You can't do it. There is no possible way. 1 over, no number will equal 0. Like 1 over what gives you 0? Infinity. Is infinity a number? Can we write 1 over infinity? My ears hurt when we say that.
Well, basically, if you do...
As x approaches infinity, y will be 0, but it'll never get to infinity. That's the thing.
Yeah, but you're going to be writing 0.000 for so long.
Right, but even that, though, it won't be 0. It'll be 0.0. Like, you could have 1 over the biggest number, and then it's 0.0000000000001. So it cannot be 0. So y can never be 0. Okay, that's cool. Is it possible for y to be a fraction? So if I put 5 in there, y is a fraction, right? Like 1/5, right? A fraction less than 1. Is it possible for y to be a whole number?
Yeah.
1 over 1, what else? Like what? 1 over 0.5. So if x is a half, what's y? 2. If x is 1/3, what's y? 3. If x is 1/5, 5, and so on. Okay, so my only restrictions then is x is never allowed to be 0 because then the function is undefined. And there are no values which will make y 0, right? So if x is never allowed to be 0, that means there is a horizontal asymptote at x equals 0. Oh, no, there isn't. It's a vertical asymptote. Oh, my. If y is never allowed to be 0, that means there is a horizontal asymptote at y equals 0. Okay? Okay. Now. Yes?
Can you combine functions so that it's 1 over root, like we've seen 1 over root x?
Yeah, like 1 over root x plus 5 and so on.
Yeah.
Yes, that's what we're going to talk about. Now we're just talking about parent functions, and then we're going to talk about transformations. Okay, another one, absolute value, right? So my thing is always, especially for like algebra 2 and stuff, I say when f of x equals root x, when f of x equals root x, I say the graph kind of looks like a square root, doesn't it? Right? It looks like the radical, right? Yeah? And then for absolute value, the graph looks like a V, like value, right? Yeah, so it's helpful for like algebra 2 and stuff. But now we're going to take it much, much, much further. So we all know, no secret, that this is what the graph of absolute value of x looks like. And so we can look at this in a whole bunch of different ways. We have here f of x is equal to absolute value of x. Okay? Now, suppose we just start with f of x equals x. What does the graph of that look like? Whoops. It looks like this, right? Y equals x. Is that what it looks like? Now, if I put absolute value bars around it, What does that do?
Y can't be negative.
Y can't be negative, so it takes every negative y value and flips it up so that this entire thing just gets reflected upwards, and now that's what it looks like. Okay? Now, guess what else about an absolute value function? It actually can be written as a piecewise function, right? Because take a look at this. If I split this up here, then look at what I have. To the right, I do have y equals x. Is that right? But if I close that and just look at the red graph to the left, what is that the graph of? Y equals negative x. So it's actually, right, y equals negative x until x is 0. So when x is less than 0, and then it's y equals positive x when x is greater than or equal to 0. And I can write that together. And so absolute value is actually a piecewise function. And in calculus, that is very, very useful. Okay? Because in order for us to be able to do things to absolute value of x, we have to look at it as two different functions. Yeah?
Could it technically be written with the greater than or equal to sign on either?
Yes. You either, yeah, you just close one, open the other. You can't have both open and you can't have both closed for absolute value. Okay. Next, greatest integer function. Nobody ever covers this anymore, and it used to be one of my favorite functions. But I did put this up just so you know what it looks like. This is called the greatest integer function. It's also called a step function. And you can clearly see why it's called a step function. And so like this shows up a lot in physics. Like for example, like if you send a pulse signal, right? That is that. Like if you just send like increasing pulse signals, you know, it's like boom, 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 boom. That can mimic a step value function. Okay. Or a step function. So the way it is, it's like f of x is equal to x in brackets, but they're double brackets. It's like they almost like ran out of signs, right, and symbols, and they're like, all right, we'll just reuse the bracket, but like make it like bold, you know? So look at this. I do like it for one purpose, for domain and range. What's the domain of this function? Huh? All real numbers. I have 2 for all real numbers. So look at this. 0 is included here. As soon as one stops, another picks up, and another, and another. It's like the ultimate relay, right? So the function exists for all real numbers. And then what's the range? So 1, 1.1, 1.2, 1.3, 1.4. All real integers. Okay, so the range is just all integers. And so the step function is that, like, if x's are between two integers, like for all x's between 0 and 1, the value is the lower integer. So when x is 0, 0.1, 0.2, 0.3, the value is the lower integer. When x is 2.1, 2.2, 2.3, 2.4, the y is the lower integer, just 2. That's what the greatest integer function does. Okay, so much for these parent functions. You noticed I spent a long time on these, which means you need to know this stuff, okay? 24 minutes and 30 seconds so far, okay? So let's move on to transformations. Transformations can affect the appearance of a graph. It moves things up, down, left, right, reflections, makes things wider, narrower, and all that stuff are transformations. Okay, we're going to start with a translation which shifts the graph up and down or right and left. Forgot that part. Okay. All right, so let's start with a vertical translation first. Okay, so suppose here you have f of x equal to x squared, right? Now, if you take your function and add a value to it, that moves it either up or down, right? So a vertical translation looks like this. So if I have, let's say, if I take my x squared, so if I write g of x is x squared plus 3, that moves my function up 3 units, right? But now if I make my g of x x squared minus 3, then it moves down 3 units. None of this is new, right? No. Okay, horizontal translations looks like this, f of x minus h. So now, if f of x is x squared again, and now for g of x, if I said x minus 2 squared, then what we do is you take that x minus 2, set it equal to 0, and x is equal to 2. Okay? Positive 2 means 2 units to the right. Okay? Now, how often do you walk in exactly equal steps? Is every single step you take equal your entire life? No, sometimes you take bigger steps, sometimes smaller ones. So these shifts are not always going to be in whole number values, right? So now suppose I have here a g of x, which is 3x minus 1 squared. I take my 3x minus 1, set it equal to 0. I'm going to make that 3x plus 1, sorry. So 3x is negative 1, and x is negative 1/3, right? So what does that tell me? Because it's negative 1/3, it moves to the left 1/3 of a unit. All right? They're not all going to be whole numbers. Okay, so we're going to use everything we've learned to graph some of these. All right. It says here to use the graph of f of x equals x cubed to graph. So just once I'm going to graph the parent function, and then we don't have to anymore. So this is an x cubed. It's an odd function. It goes up on one side, down on the other side. Okay, if it's positive, so here's the center. It's positive x cubed. So if I go in the positive direction 1 unit, it goes in the positive direction up 1 cubed. And if I go in the positive direction 2 units, it goes up in the positive direction 8 units. So that means if I go in the negative direction 1 unit, it's negative 1 cubed. So I go down negative 1. And if I go negative 2, I go down negative 8. So finally, oh my gosh. It won't. I don't know why it won't right. Okay, right? All right, so what does the other function do? X cubed minus 3. It goes down 3. So the center moves down 3. So basically every single point is going to move down 3. Now, if you started from there, the change is the same. A positive change of 1 unit in the x will be 1 unit in the y. All right, and then a positive change of 2 units will be 8 units in the y. So from here, if I go up 8, I go to 5. And then if I go left 1, it makes my function go down 1. Left 2 means down 2. So essentially, if you look at it, let's turn out right. So if you look at it, every single point moves down the same amount. Okay? All right, so what about the other one? Uh-huh. And to the right 4. So up 2 and to the right 4. So right there. Okay? So from here, if I move over 1, I go up 1. And if I move over 2, I go up 8. And similarly in the opposite direction. Now, on the test, if I ask you to show, okay, if I ask you to label your coordinate points, let's say I asked you for 3 coordinate points, put in 3 coordinate points. So this is 4, 2, 5, 3, and 6, 10, right? You're obviously going to have to put in additional points to graph, but you don't have to give me the coordinates of those. Does that make sense? Okay, so how about reflections? All right, so a reflection, right, if this is y equals root x, a reflection in the y-axis or in the x-axis happens with a negative in front. So if this is root x, then this will be g of x is equal to negative root x. Okay? And here we already talked about this. So if I have y equals root x, that exists over all of the x values, which are positive. But now if I make it g of x equal to root negative x, now that only exists over the negative values of x, right? So it's a reflection, and that's why it's a reflection. Yeah.
One doesn't matter because sometimes you can lie.
It doesn't. I tried. I'm trying to like switch so that it's always.
Yeah. And also because since even though those don't exist, those aren't actual functions. Like if the one in the reflection on the x-axis, even though it's not a real function, it's okay. When you're asking for the reflection because.
Oh, it's a real function because y equals root x, it's only the blue.
I know, but then when you do the reflection, it's still...
When you do the reflection, yes, because now it's only the green when you do the reflection. Yeah. Okay, yeah.
Is there an equation for that? Like both parts of y equals x squared and the opposite value of x?
This one?
Yeah, like for the entire line.
There is. There is. Okay. So we're going to use f of x equals root x. So remember what root x does. For every change in x, it goes up or down like the square root of it, right? So this one is negative root x plus 4. So let's just graph what root x will look like. The end point is at 0, 0. And then if I go over 1, I go up root 1. If I go over 4, I go up root 4, which is 2. If I go over 9, I go up root 9, which is 3. So that's what it looks like. Okay? That's what root x looks like. So now let's graph h of x. H of x has a shift up 4 units. So the endpoint is now here. Now, what is the function going to do? It's still going to take a square root, but then make the value negative, right? So if I go in the positive direction 1 unit, it's going to give me the square root, but in the negative direction, so down here. Okay? Because it's negative root x, it reflects downward. Okay, so think about what it does. It takes your value, gives you the square root, and then makes it negative. So I go over 1, the square root is 1, the negative of it is negative 1, downward. So if I go over 4, 1, 2, 3, 4, the function takes the square root and makes it go down 2 units, so right there. All right, so that's what h of x looks like. And now what about this one? Here, the function, the endpoint is moving to the left 1 and up 2. So I'm going to start here. And what does the negative do? It's a reflection around the x-axis. All right, so now, again, same thing. If I make a positive change of 1 unit in the x, my y goes down 1 unit. Positive 4 goes down 2 units. Positive 9 goes down 3 units. Okay?